All right. Yeah, so hello everyone. Welcome to the lecture 4 about waveguides and waveguiding devices, right? And as usual, we start with a brief recap of the last lecture. Um, so, mm, right, let me repeat the Maxwell equations. We will use them today. So in the general case, the first Maxwell equation is the Gauss law that describes the source of electric field, right, as a function rho, which is the density of electric charge. The second Gauss law for the magnetism says that no magnetic charges uh, in nature. Faraday's law for induction, which was the main one for the previous lecture, says that, okay, if you have magnetic field changing in time, it will unavoidably create the curl of electric field. So changing of magnetic field creates electric field, just like a, in a loop of wire loop, right? Changing magnetic field in that loop creates the current or the electric bias, electromotive force. And finally, the Ampere's law, which connects the change of electric field in time to the curl of magnetic field, and also says that any current unavoidably creates this uh, magnetic field. All right, so using these Maxwell equations, last time we derived as one of the consequences of these Maxwell equations, we say that, okay, even in an area of space without any currents, any charge, right? Like I cross out this part here, I have only electric and magnetic fields. So the change of electric field in time creates magnetic field, which is also changing in time. So in its turn, it creates the electric field and so on. So it's a self-sustaining process, which we call the wave, right? The electromagnetic wave. One field creates another one in the next uh, place in space, and then that field creates a new field and so on. And this field propagates in space with the phase velocity c, which is uh, the speed of light, right? Is the very famous constant. Essentially, it's the largest velocity uh, in space. I mean, in nature. Um, yeah. However, mm, from the practical point of view, it's not always kind of beneficial to transfer electromagnetic fields, electromagnetic waves in free space, right? So in free space, we often have some objects that interfere with our waves. So from the practical point of view, we can use some wave guiding devices. Okay, so today we will be talking about, well, transmission line, and also as a generalization of transmission lines, we'll be also discussing rectangular waveguides, which is, by the way, looks like this in the lab, coaxial waveguides, very briefly, but there is a very important difference between rectangular and coaxial, so we need to mention that. This is how coaxial cable looks like in reality. And I mean, optical fibers, you know that light is another manifestation of electromagnetic field, right? Light is also electromagnetic wave, and we can use waveguides not only for microwave, but also for guiding optical fields, guiding light. To do so, we use optical fibers. We are not going to talk about optical fibers today. It's a subject for another course, photonics and so on. But these optical fibers are very important because, well, today the vast majority of information of internet is transmitted using optical fibers, and without optical fibers, we wouldn't be able, for example, to handle this lecture with Zoom. All right, so to begin with, let us discuss transmission lines. Right, the transmission line is a very simple structure. It consists just of two metallic wires, closely spaced metallic wires. So these wires, being metallic, being conducting, support current along each wire, and this current changes in time. It creates electric field and magnetic field around these wires. And this system does not support any type of electromagnetic field, okay? It supports only wave guiding modes. So what is this wave guiding mode here? Okay, so if you consider a local area of this transmission line shown here in red, the upper wire supports current, and let's say in one time instant, this current goes from left to right, okay? This current oscillates in time, and as we will be talking in the next lecture, any oscillating current creates electromagnetic field, so radiation, right? So it doesn't work for transmission line for the wave guiding mode, because if current creates electromagnetic field, it will be radiated and not transmitted. So this is not the field we after. Eric, do you have any questions? Okay, if not, then try to mute yourself. So oscillating current radiates. We need to cancel this radiation out. To do so, the lower wire, the second wire, must support the same current, but oscillating in the opposite direction. Okay, so only in this way, the upper current will radiate with one phase, the opposite current in the lower wire will radiate with the opposite phase, and these two radiations will be canceled down, and the entire structure as a result won't radiate but guide electromagnetic field. Okay, so only this type of field can propagate along this system. Okay, how we describe such a system using math, right? Mathematics. To do so, we introduce these distributed parameters, including resistance of the wires. So we assume that these wires might be not perfect, so they have some resistance. Inductance, right? Any wire gets inductance. This parameter we discussed last time. What is inductance? So basically, if you have a wire, you try to change the current in this wire, but the wire itself interacts with itself, right? So it resists to the change of the current. This is the source, this is the nature of inductance, of self-inductance of these wires. Conductance of the surrounding area, this can be air or some type of dielectric, and of course this is not perfect, so we take into account this conductance and the capacitance between two wires, right? So one wire can store some charge, another one can store some charge, and this capacitance describes the charge that the system can store when you place these wires together. Right, so these 4 parameters in every single point of along this transmission line allow to describe analytically the system. So introducing these parameters, it allows me to write the RLC circuit scheme diagram for the element dx or dz of my transmission line. Okay, so for every single small dz, I have R, L, G, and C. And R and L connected in series because it is attribute of the wire, right? And the shunt elements G and C, they are parameters that describe the coupling between two wires. So they placed in parallel, right? Or shunting elements. And the variables I am after are voltage and current on the left, and how they connected to voltage and current on the right of this small element of transmission line, right? So yeah, having this circuit now, I can write the Kirchhoff's voltage law, right? If you forgot, Kirchhoff's voltage law is simply the statement of energy conservation law, right? So energy conservation law. If you draw a closed path, like shown here in red, the total voltage drop, right, along this closed path must be equal to the electromotive force in the circuit. Here we have no electromotive force, so this voltage must be equal to the difference of the it must be equal to 0, but as I go clockwise along this path, so here I get V, right? Then I got the voltage drop across the resistor, and then which is this term here, then inductance, which is this term here, right? This is simply the electromotive force that is induced in the inductance. Compare this formula with the formula from the previous lecture, right? And then minus this voltage along this path 4, and that's it. Yeah, so this is the total Kirchhoff's voltage law. I can divide this formula by dz, right? This is the result, and then I assume that this dz element length is very small, so it allows me to introduce the partial derivative dv over dz, and this is the result. So it's a voltage equation. It's pretty simple. Similarly, I can write the Kirchhoff's currents law. Again, I remind you that Kirchhoff's currents law is written for any node in the circuit, right? So I can, for example, consider this node over here. And so the current, Kirchhoff's current law is the statement of charge conservation law. Simply charge conservation law, meaning that if you have a node, the amount of charge that comes to the node simply equals to the amount of charge that goes out from this node. Charge conservation law. If I consider, for example, this upper node here, I immediately see that the current IZT that comes to this node from the left is equal to the current that goes out from this node, IZ plus ZT, right? And plus the current that comes from this part here, from this line, which is equal to the sum of current that goes through this conductance of the material between the wires and through this capacitor. So this is the sum of two. Again, I divide by delta Z and make this delta Z very, very small. So again, I can rewrite this in terms of partial derivative of Z, and this is my current equation. So for now, they don't remind me anything. These two equations, they just connect the change of voltage across some small element of my transmission line to the change of the current in time, and vice versa here. If I take the special derivative of the first one and then substitute the second one to the first one, I will get this equation here. And similarly for the second one, I will get equation like this. Still doesn't look like anything similar for me, but if I assume that my wires are very good, they don't have noticeable resistance, and my conductance of this space around is also negligible, so then I can neglect these underlined parts here and here. And as a result, assuming that G and R are negligible, right, I come to these equations which look exactly like the wave equation for the electromagnetic wave. These two, right, is up to the change voltage by electric field and current by magnetic field. So I conclude that this transmission line can support electromagnetic waves, right, that propagate along the transmission line, and the phase velocity of the system is 1 over square root of LC, right? So tailoring the system, these parameters L and C, they are parameters of the wires and their coupling. I can change and I can manipulate the velocity of my traveling wave. Okay, so I can, for example, make it smaller to slow down the electromagnetic wave. But in the general case, these equations here are pretty complex, but I can use this useful approach of phasor or phasor domain, right? So you're of course familiar with this. I just remind you that the phasor is a simple assumption that my field or voltage and current depend on time as a e to the power of I omega t, right? So it's a harmonic signal, harmonic function. And according to the Euler's formula, it is simply cosine omega t plus I or j sine omega t, right? So it gets real part and imaginary part. I can use this formula, just remember that after my calculations, I need to take the real part of the final solution. Yeah, so I use this phasor domain representation for the current and voltage, plug in this to these formulas, and the general solution for the phasor amplitude v tilde, right, is equal to this two terms, this sum of these two terms, v plus and v minus, which essentially the wave that propagates to the right and to the left. Similarly, for the current, we get these two terms here, which looks like solution for the voltage, but divided by Z0. So this Z0 is a pretty important parameter. It's called characteristic impedance, right? I mean, if you divide voltage by current, you get impedance. So this characteristic impedance defines basically the parameters of this transmission line. And this gamma small is propagation constant, which gets both real part and imaginary part. If you forget real part for a moment, propagation constant will be purely imaginary. And if you plug in this gamma here, imaginary, it will be simply harmonic function as a function of z. Right? Z is a coordinate, so it will be sinusoidal wave along these wires. However, we also have this lambda. Lambda describes the dissipation or decay of the amplitude. Yeah, so if my system is lossless, R capital and G capital 0, then my gamma will be purely imaginary and wave will be propagating without any dissipation along this transmission line. So these two parameters are pretty important. We won't use them, but these two parameters that describe any transmission line, right? So we have a system, transmission line, that can support a traveling electromagnetic wave, right? This system is described by characteristic impedance and propagation constant. So what happens if we abruptly modify or change or just stop, right, cut our transmission line, forming the edge, right, the boundary. Let us consider this system now. So suppose I have a transmission line shown here in black, and then abruptly at coordinate x0, I have a end of this transmission line, and I can connect some load to the end of transmission line, and I describe this load by Z load, ZL, which can be complex. Okay, so it's this load is some sort of a device. It can be antenna, it can be something else. so some load. My transmission line supports this wave for the voltage. It's a V plus wave propagating to the right, and V minus propagating to the left. And similarly for the current, I have two waves to the right and to the left. But here at the end, right, I know that the impedance of this line must be equal to the impedance of the load, right? So impedance of the load from the one side, from the other side, this impedance must be equal to the voltage at this point over current at this point, at the end of this, at the terminal of this line. The same time, this voltage at x0 is equal to the V plus V minus, or the amplitude of right propagating and left propagating waves at this coordinate at the terminal, and the current as well. So I plug in these two formulas to this equation here and factorize this z node. Next, I can introduce the reflection coefficient. By definition, reflection coefficient is just the voltage that is propagating to the left, V minus, divided by voltage propagating to the right. Voltage propagating to the right is a signal that I'm sending to the system. Suppose I have some generator, for example, here on the left side, right? That this wave propagates, reflects, and returns back to the generator. And this is left propagating field, which is V minus. So introducing this coefficient, we can rewrite this upper formula in this form, and then I can rewrite everything in terms of gamma capital, which is reflection coefficient, and I get this simple yet very important and very useful formula for this waveguide theory, analysis, and applications. Reflection coefficient is a ratio of difference of the loading impedance and characteristic impedance to the sum of these two impedances. So let us consider several important special cases. So one special case is a case of matched load. From this formula, it's easy to see that in order to get rid of reflection, we just need to make a phase matching. Right? It's the transmission line characteristic impedance must be equal to the load impedance. So in this case, the reflection coefficient is 0, meaning that everything that we send to the system doesn't return back to us, to generator, and so on. So this is a matched case, matched load. Very important case because in the vast majority of applications, this is the case of interest, right? We design the system in a way to get rid of any reflections, because reflection can be a sort of loss, right? If signal reflects back, it is lost, or this, in the case when this reflection is strong, it can even break our generator and so on. So important case, this matched load. Similarly, for the short circuit, so we just connect these two wires through, for example, a piece of wire. So something that has a negligibly small impedance, right? In this case, the reflection coefficient is equal to -1, and this is the case of reflection of wave, like from metal, right? Like from a mirror. Mirror, we use this perfect metal, right? And the wave just reflects back to us from this metal. Reflection coefficient is equal to -1, which means that the reflected wave is in out of phase, in the opposite phase to the coming wave. Okay, so this superposition of coming wave and the reflected wave creates the standing wave in this case, which looks like this. Okay, so it's a let's say blue is coming, red is reflected, and then black is the superposition of both. Okay, so it's a just a standing wave that let's like this from -1 to 1. And finally, open circuit, meaning no load at all, right? So just the end of the transmission line. So in this case, the load impedance diverges, right? And the reflection coefficient is equal to +1, which is also standing wave, but standing oscillating from 0 to 2, something like that. Do you have any questions about this part? Awesome. So, as I said, this load, this ZL, might be any kind of device. It can be antenna, it can be probe, it can be like whatever it is. And you see that the reflection coefficient depends on this load impedance. It means that you can measuring reflected coefficient, you can do the measurement of, for example, characteristics of antenna, or it can be some sort of a sensor, and then measuring reflected wave, reflection coefficient, you can do some sort of sensing and so on. So it would be, I mean, it's very important to be able to measure this reflection coefficient. And to do so, we have a device. It's called Vector Network Analyzer, or VNA in short. So VNA is a nice device. Essentially, so this is a picture of a typical VNA. It's a 2-port VNA. It's a single first port and a second port. To measure reflection, we need only one port. It's enough to have one port. So this device basically generates a very stable frequency harmonic signal, sends this signal to this waveguide here. Okay, and this device knows everything about this waveguide, so it normalizes everything to the characteristics of this waveguide, and then it comes to some sort of device. As I said, can be antenna, whatever. Some energy transmits, some reflects. So it measures the reflected wave, the wave that returns back to this VNA, right? And comparing the two, it calculates the reflection coefficient. In terms of VNA, this coefficient is called S11. Okay, so it's S11 is the same as gamma capital. So the same thing. And here, this picture describes what happens, right? You have input then this input comes to the device on the test, right? Part of the energy of the wave reflects back to the first port. Another part goes through the device. Okay, so this S11 is the reflection coefficient that we just discussed. Okay, and the typical result of the experiment looks like this. So it's a magnitude of this reflection coefficient in terms of dB. Okay, so you send 1 watt of power, the wave with power of 1 watt, and then this curve describes how much energy returns to you, returns to the generator, returns to the VNA. The smaller this value, the smaller wave returns. And for example, if this is the result of measurements of an antenna, here it means that antenna doesn't reflect, it actually works as an antenna, it radiates. We'll be talking about antennas next time. Yeah, so this is kind of important to know. Do you have any questions about this part before we start discussion?
Doctor, so now I've heard of a device called SNA. What's the difference between an SNA and a VNA?
Excuse me, could you repeat your question?
What is the difference between SNA and VNA?
So this is this letter V here. It's a vector network analyzer. So basically, it means that this device can measure the phasor, right? The entire information about the phasor. So this phasor domain, you see it represents a vector in the complex plane, which gets magnitude and phase. So this vector network analyzer simply means that it can measure not only magnitude, like shown here, but also the phase, which is another very important characteristic. The phase of your reflected wave. Yeah. So this is the main difference. Yeah, and in order to be able to measure phase, it is actually not a simple task, because you need to know exact phase that comes out from your port, right? So you use that phase as a reference. It's called phase locking. So it's a phase locking, and to do so, it is pretty challenging. For this reason, basically, this VNA is a quite expensive device. Okay, so the VNA I have in my lab, it can cost maybe 30, 50 thousands of dollars. So it's a expensive system, exactly for this reason, because you need kind of very stable generator and phase locking system to be able to measure phase. Is this answering your question?
Yes, thank you, Doctor.
Okay. Yeah, so rectangular waveguides. Rectangular waveguides looks like this, right? It's rectangular system consisting of metallic walls, right? In X and Y, it is restricted in X and Y, and then in Z, it is extended system. So the wave can propagate along this waveguide along this z direction. In general, this waveguide can be filled with some dielectric, epsilon and mu, but in practice it's not very useful and very feasible. So typically this waveguide is empty. Okay. Since this wave propagates along z, the solution to these waves is simply depends on z coordinate as a harmonic function, right? E to the power of minus j beta z. Beta is a propagation constant. Beta is a propagation constant. E and H fields, electric and magnetic field, they they vary in xy plane and can be different function. All right, and and typically we assume that the walls of this waveguide are made of perfect electric conductor, PEC. Okay, so it's like a perfect, very good metal, so highly conducting metal, which simply means that any component of field and the special derivative of this field is equal to 0. Okay, this is from the boundary conditions. So it means no field inside the metal. If no field inside, just across the boundary, then this field must be equal at the boundary, at the wall. Okay, so this is the assumption we usually take describing this rectangular waveguides. In order to describe this rectangular waveguide, we again start from Maxwell equations. The derivations quite bulky, and of course I'm going to skip them. If you're interested, you can. I refer to those chapters in that book. But here we are discussing just the main aspects, right? So Maxwell equations in the time harmonic domain, right? So the difference comparing to the equations that we already discussed in one of the previous lectures is this mu and epsilon. We also discussed them, right? It's dielectric permittivity and permeability, magnetic permeability. But again, usually this mu and epsilon simply equal to 1. Well, they are equal to the constants, the dielectric permittivity of vacuum and magnetic permeability of vacuum in this case, right? So taking the curl of the second one and then substituting the divergence for the electric field to the result. This something that we already did for this for the electromagnetic waves. This is the result, right? The Helmholtz equation for magnetic field, and exactly the same equation for electric field. This one for magnetic field. Here it's we can introduce this value, right? Omega square times mu epsilon. We denote this as a k square, which is wave number squared. It turns out that well, let me say this this way. So this waveguide, it can support the field with of very different configuration. Okay. At the same time, the system is linear. It means that the sum of two solutions is also a solution. Okay, for this allows us to describe two types of waves in this rectangular waveguide, namely transversive electric mode and transversive magnetic modes. So transverse electric mode is a mode with vanishing electric field along propagation. Okay, so EZ equals to 0. Similarly, for magnetic TM mode, it's a mode with magnetic field component Hz equals to 0. Okay, so the general solution is a combination, the superposition of two. But we can consider these two cases independently because the system is linear. Okay. We will be discussing just this one, TE, because it's a kind of more important case. The discussion for the TM is exactly same. So let us look at this waveguide, the Helmholtz equation here. We can write this equation for the Hz component, right? And taking into account that the Z coordinate, the magnetic field depends, the Z component of magnetic field depends on Z coordinate only through this harmonic function, right? So we can immediately take this Nabla operator, or which is the partial derivative by Z, which gives us this beta squared. Okay, so yeah, the result is this: for the Hz components of our waveguiding mode, which depends on Z coordinate only through this harmonic function, this is the result. We can introduce this notation KC, which is cutoff wave number. Cutoff wave number. Why it's so important? It's important because from this notation, I can derive beta, which is equal to square root of k square minus kc square. Okay, k is a wave, any wave number of the propagating waveguiding mode. Okay, which is essentially the ratio of the phase velocity to the angular frequency. So beta is equal to square root of k square minus cutoff wave number squared. So it means that in order to be propagating this waveguiding mode, right, look at this solution here, this general formula. If beta is real number, then this e to the power of j beta z is a sinusoidal and sine and cosine function, right? So it's a propagating sinusoidal field. However, if beta is imaginary, then this imaginary unit goes away, right? And this function will be decaying, namely exponential decaying. So it's a not propagating field, right? So waveguiding mode is a mode with real valued beta. And to do so, for that, this omega square mu epsilon must be greater than cutoff wave number. Or similarly, the frequency, this linear frequency phi, must be greater than some cutoff frequency for this particular mode. Okay, so this is important. This is the statement of the fact that this rectangular mode is not supporting any frequency, the field of any frequency. The frequencies, the field with frequency smaller, lower than cutoff frequency won't propagate in this waveguide, and only fields with frequencies greater than cutoff frequency will propagate. Okay, so skipping the kind of bulky calculations, we just write down the final solution for the magnetic field. For the electric field is basically the same. It's a product of cosine function of coordinate x, okay, and the cosine function along the coordinate y, this vertical direction here, with m and n, which are numbers 1, 2, 3, 4, and so on. For the cutoff wave number, we get formula like this again. So you see it's defined by this m and n, integer numbers, and also defined by a and b, which are the what's called the width and height of this waveguide. And finally, for the frequency, for the cutoff frequency, we got this equation, which again depends only on the mode number mn and the dimension of this waveguide a and b, width and height. Very important statement result is the fact that the very first mode of a rectangular waveguide is a TE 10 mode. Okay, so M is equal to 1, N is equal to 0, right? And in this case, if you substitute M and N here in this formula, you will get C over 2A. Okay, so it's this is the lowest cutoff frequency. Okay, so below this frequency, no traveling modes. Above this frequency, we can excite TE10 mode, and as we go higher in frequency, we can excite TE20, TE21, TE30, and so on and so forth, depending on this formula. But this is the lowest possible cutoff frequency. So in your simulation, you will be calculating the waveguide around this cutoff frequency, and you will see that below this frequency there is no propagating field, no propagating mode. The field will be just decaying in space, but just above this frequency, you will see this nicely propagating waveguiding field. Yeah, and this is how it looks like for TE10. So you see one change of electric field, right, along the, oh, so it's an electric field, so it's not very representative. what is more representative is this picture here. So for TE10 mode, this is the electric field distribution here, and this is magnetic field distribution. So you see, according to our result, according to this formula here, TE10 mode doesn't change along y direction. Okay, so it's a constant along y, the field, and has exactly one change in the x direction, in the width. Similarly for electric field, constant along y and one change along x. For the 2-0 mode, similarly, 0 means no change in the y, and exactly 2 total change in the x direction. It changes twice here. And similarly for TE01, no change along x direction, and one let's call it one total change, one half of the half, one total change in the y direction, right? For the electric field and for magnetic field. And this waveguide can support other modes, TE3, 1, 4, 0, 5, and so on and so forth. And also here we have this distribution of current. Current, of course, distributed on the surface of the waveguide, because the inner area is not conducting, only the walls conducting. You see that the current also inhomogeneous, okay, as supposed to be. What would be important here to mention is also often current has some zeros on its surface, right? For example, here at this top surface, top wall, I have the 0 of current. It means that if I make a cut here in this area, this cut won't change the mode, this TE10 mode, because the current was 0 there. And similarly, in any area of vanishing current, I can make a hole, I can make a cut, and that won't change the mode itself. But for other modes, of course, it will change it, because the current might be not vanishing in the other place. Okay, so for example, can you define the type of this waveguiding mode, right? Along y, how many changes? It's one total change, right? So it's y supposed to be 1 here, and in the x direction it is 1, 2, and 3. So this mode is TE 3, 1. Okay. In practice, these high order waveguiding modes never used. They have some dispersion and so on. So it's more kind of preferably to use low order modes. TE10, for example, this is the most used type of mode in practice. Do you have any questions?
So, doctor, what you're trying to say is if I had a frequency in a rectangular waveguide that's lower than the cutoff, it won't propagate whatsoever. But if I have frequencies above it, it will go through, but only certain frequencies will go through. Not all of the frequencies above the cutoff will go through, only certain ones, and it depends on the equations which ones will be allowed.
Yes. So it's defined by this formula here, this formula for the cutoff frequency depending on the mode order and the size dimension of the waveguide. So below this fundamental mode, you won't have any modes propagating, right? No modes propagating below this frequency. Just above this frequency, but before the second mode, which will be TE, I believe, 1, right? There will be only one waveguiding mode. As you go higher and higher in frequency, you will add more and more high order modes to the fundamental one, but fundamental will be there. Fundamental will be there, but you will getting more and more high order modes. Yeah, so you probably will see that in the simulation of these waveguides. Okay, so a few words about coaxial cables to conclude today's lecture. Coaxial cable, coaxial waveguide is used much more often than rectangular waveguide. It's a very nice waveguide for several reasons. So here is the geometry of this waveguide. As you can see, it gets this outer cylinder, right, and this inner conductor. And the presence of this inner conductor is important because its presence makes this waveguide cutoff free. Okay, so this waveguide has no cutoff frequency. It means that this coaxial cable can support any frequency from DC, from 0 frequency up to any frequency up to the, some natural limitations like this material breakdown and so on. So any frequency supported by this type of waveguide. This is because the modes supported by this waveguide are TEM, so transverse electric and magnetic modes. It means that not only electric field has no component to along the propagation, or magnetic field, no magnetic field along the propagation, for as we had for TE and TM modes, right? But both electric and magnetic field, they both have vanishing component along propagation direction. So it's a TEM type of mode. So this type of mode has such a profile, electric field radially distributed and magnetic field circularly distributed around this inner conductor. At the same time, the structure is pretty simple. It depends, the characteristic impedance of this waveguide depends on solely depends on the geometric parameters of this waveguide. B is the outer radius and A is the inner radius of inner conductor. So changing these parameters allow you to design this characteristic impedance in wide range. Of course, the most important common values are 50 ohm, which is the standard, and 75 ohm, which used to be a standard for TV antennas and so on, because 75 ohm is close to this dipole antennas. Okay. Today the standard is 50 ohm. Everything is calibrated to 50 ohm. Okay. This cable supports very like handy and useful connectors, right? Two versions. BMC is one type of connector. This connector is kind of low frequency connector. We use it for oscilloscope, for example, or some low frequency generators, right? And more popular is SMI connector, sub miniature version A connector, which can support frequencies up to 20 and actually higher and higher frequencies. Male and female, if you come to my lab, you will see a lot of them. I mean, these coaxial cables with this semi connectors. Yeah. So what else to mention here is for example, if you have so this coaxial cable has no cutoff frequency, right? So a particular waveguide can support any frequencies. However, if you, for example, start from a fixed frequency and then will shrink the size of the radius of this waveguide, it will be still supporting this waveguide, but it will increase more and more the electric and magnetic field of this mode here. So it means that this waveguide actually can be useful in terms of, I mean, for the applications where you need to increase electric and magnetic field in a local area. And in fact, people use the end of coaxial cable for example, micrometer resolution sensor. Okay, so you can make a very tiny, small coaxial cable and use it as a microscope to measure some very small, very little objects, because for this reason, it localizes the electromagnetic fields highly and strongly. But this is just another kind of application. All right, so the next lab will be about simulating rectangular waveguide around cutoff frequency. Right, I already made that assignment. Some of you already started working on that. I apologize, I was not able to record this the tutorial. I will do very soon. So thank you, and let me stop the recording, and then maybe we can quickly discuss.